The following video is on derivative shortcuts. This is part 1 in this series. Last time we saw that the definition of the derivative of f of x is the limit as h goes to 0 of f of x plus h minus f of x over h, provided that the limit exists. F prime of x represents the slope of the tangent line to f of x at the value x. Today we're going to learn some shortcuts for evaluating derivatives. The first one tells us that if f of x equals c for some constant c, then the derivative of f of x is 0. Let's look at the proof of this. So we're going to use the limit definition of the derivative of f. So that is the limit as h goes to 0 of f of x plus h minus f of x over h. And because f is the function c at every x value, we end up with the limit as h goes to 0 of c minus c over h. This simplifies to the limit as h goes to 0 of 0 over h. So as h gets very close to 0, this fraction is always going to be equal to 0. Thus we get that the derivative of f of x is 0. Let's look at some examples. So if f of x equals 7, then f prime of x is 0. And if we look at the graph of f of x equals 7, it's a horizontal line. So we see that the slope at any point on this line is indeed 0. Looking at another example, f of x equals pi. Pi once again is a constant, so if we take the derivative, we end up with 0. For our second theorem, we have that if f of x equals x, then f prime of x will be 1. Let's do the proof of this. Once again, we're going to start with the limit definition of the derivative, and in this case, the function is always going to spit out whatever is being plugged in. So we end up with the limit as h goes to 0 of x plus h minus x over h. Notice that the x's cancel out of the numerator, and we're left with the limit as h goes to 0 of h over h. Well, h over h is the same thing as 1, so the limit as h goes to 0 of 1 is just 1, which is what we claimed it would be. Another theorem, if f and g are both differentiable, d by dx of f plus g of x is going to be d by dx of f of x plus d by dx of g of x. In other words, the sum of the derivatives is the derivative of the sums. Similarly, we can do the same thing with the difference. So instead of addition, we can do subtraction, and it'll still hold. The proofs are going to be done in class, so we will hold off on those. Our next theorem is the power rule. If f of x equals x to the n, then f prime of x is going to be n times x to the n minus 1. So we bring the exponent out front and subtract 1 from the exponent. The proof of this we're just going to do for integer values of n, and we need to remember the fact that a plus b to the n is the same as a to the n plus n times a to the n minus 1 times b plus dot 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 to b to the n. This is a fact that you should have seen in your Algebra 2 class in high school. The most important thing about this is that all of the last terms of this sum have at least a b squared in them. So using the limit definition of the derivative, we can simplify everything out to end up with n times x to the n minus 1. And I know that this proof went by very quickly, but you're not going to be tested on it. This is mostly just to verify for you that this actually works. Let's look at some examples. So if I have f of x equals x to the 15, The derivative of that, we're going to take the exponent, which is 15, we're going to bring it out front. So we'll have f prime of x equals 15 x to the, and now we're going to subtract 1 from the exponent. So 15 minus 1, which gives us 15x to the 14. Here's another example. F of x equals x to the pi. Pi is just a constant, so we bring the pi out front, subtract 1 from the exponent. So we'll get pi times x to the pi minus 1. Another example, if f of x equals x, notice that that's the same as saying x to the 1. So if we take the derivative, we bring the 1 out front, subtract 1 from the exponent, which gives us 0. And notice that that's the same thing as 1. X to the 0 is the number 1. So this is the same as what we saw before when we learned that the derivative of x was 1. Another theorem, if our function g of x is a constant c times f of x, then g prime of x is going to be c times f prime of x. In other words, if we have a constant multiple, we leave the constant there and take the derivative of everything else. The proof of this is simple. We take the function g and replace it with c times f. We can pull a c out of every term in the limit, and we're left with c times the definition of the limit definition of the derivative. So we end up with c times f prime of x. Once again, this went by very fast, but you're not going to be tested on it. It's just important to have seen it once. Let's do an example putting all of our laws together. Let's start with something like pi times x to the 7th. So pi is a constant multiple. We can just leave it there. Then we just take the derivative of x to the 7th. So f prime of x is going to be pi times the derivative of x to the 7, which is 7 times x to the 7 minus 1, or 7 times x to the 6. So we end up with 7 pi times x to the 6. Another example, let's do f of x equals 3x squared minus 5x plus 17. The derivative of 3x squared can be done separately from the derivative of 5x and the derivative of 17. Those are using the sum and difference rules. The derivative of 3x squared is 3 times the derivative of x squared, which will be 2 times x to the 1. The derivative of minus 5x is minus 5 times either x to the 0 or just 1. And the derivative of 17 is 0. So simplifying this, we get 6x minus 5.